Good morning, everyone. So today we'll look at, so this is class 7 for design of optimal design of cleaning systems. So last 6 classes we saw how to design cleaning systems for M1 queues. And we looked at steady state averages for all the systems. So steady state design. So now we'll shift the problem to um, designing the scheduling policy at each time. So as we discussed in last class, the performance metrics dependent on the arrival rates or the service rates and also scheduling policy. In the last 6 classes, we saw different uh, variations of changing arrival rates and service rates. So we have precision variables and known variables from the both arrival rates and service rates. While we fix the scheduling policy as a FIFO scheduling policy, first and first policy for MMLQs. Now, what we'll do is we'll try to find the best scheduling policy so as to optimize some performance metrics. Right? But scheduling policy uh, is basically some action that you take or you decide which of the flows to serve. So scheduling policy usually comes when there are more than one flows and you have more than one queues. Right. So the basic design of scheduling policy would be you have two input flows and you have two input flows with two different queues, but you have a single server which can serve or a single channel or a server which can serve one of the queues at a time. So you switch between one of the queues at each time instance. So basically now instead of steady state analysis, we are doing time based analysis, right? So the same way in the last class we saw how the cost function that we used, the cost function was just expected cost at steady state. For the design of scheduling policy, we will convert this to um, time averages. We will optimize the cost function, which are basically time averages. So this is Q1, this is Q2, A1, A2 are arrivals, and you have a service or a channel, which will serve only one of the queues. Now you need to decide which queue to be served at time slot. So basically, we will be looking at general stochastic optimization problems. So the general stochastic optimization problems that we'll be looking at, we'll mainly consider uh, cost function, which is a time average function. Uh, we'll have constraints, which is also time average. So first we'll just discuss the general setting of this, and then once we've discussed the general setting, we will go into details what each of the functions mean. So in the general setting, we'll have a network which functions in discrete time. So you'll have time instance 0, 1, 2, and so on. So at each time instant, something will happen in the system. Like there will be some change. Either some arrival packets will come, or some packets will be served. The queues of each of the servers in the network would be updated. Something like that would happen, right? So how do you characterize the whole network is by uh, their queue backlogs. Queue backlogs that is written in a vector form, capital QT. This is a vector of the queue lengths at time t for each of the queues present in the network. So we'll assume there are k queues present in there, where k is a non-negative integer. Right. So at every slot t, at every slot t, a control action is taken. And this action affects the arrivals, departures, and also creates an collection of some vectors x, y, e. So these vectors right now are just some vectors which could give you an insight on the performance metrics of the whole network. So what you have is you have xt, which is a vector x1t and so on to xmt. Some performance metrics which is measured across n nodes or something. This I'm giving a general outlook. We'll later define what x, y, e, all of these are. Y0t, Y1t, YLT, E1t, EJT. So these are all vectors with different lengths. Where each of them are some attribute of the network at time t, right? And M, L, and J are non-negative integers. The attributes themselves can be positive, negative. They can represent some penalties or rewards that is associated with uh, each of the uh, networks at slot t. Some examples of these vectors could be something like power expenditure, distortions in the channel, or packet amount of probability of packet dropping, and such other. So basically, these each element of these vectors is a function of your arrival function, right? And some randomness either in the channel or the randomness in the arrivals and the control action that you have taken at time slot t, right? So the control action that you take is whether you want to put your communication packet into the channel or not. That is your control action. So each of these vectors, I'll remove the x and t is vector. So this is basically a function of alpha t and omega t. This is for all n belongs to set of. Similarly, you'll have the same for y, y and t. Function of the control action that you've taken at time t. The randomness in the server belongs to set of. So here omega t is the random event that has occurred in your system at time. Similarly, alpha t is the control action that we have taken at time t. Okay. So basically, the random event that has occurred in your system at time t could be a random arrival of a packet or packet loss due to channel condition in a wireless system. The control action is basically deciding or choosing. So it's basically deciding if a packet is communicated or choosing which packet must be communicated. So from now, the most general thing I'll make is alpha t is basically a set of actions that you have a set a omega t. So depending on what has happened at that time instant t, you will generate a set a omega t of actions that you can probably take. Right. So based on that set, you'll pick one of the actions from that set and you'll execute that action. So, okay, so this is the basic general overview of how you mathematically model the whole network using queue backlogs and then generate uh, attribute vectors for the networks with different attributes depending on the control action at time t and the randomness in the network at time. Right? Now we'll define x m bar, y m, y l bar, and EJ bar. So XM bar is time average. Limit t tends to infinity 1 by t summation I equal to 0 to t xmi. Similarly, yl bar is limit t tends to infinity 1 by t summation I equal to 0 to t yl I, and similarly promote EJ bar. Now, the first objective is to design an algorithm that solves the following problem. So we minimize y0 bar subject to yl bar less than or equal to 0 for all L belongs to set of 1 to L. So these YLs are your set of your attribute vectors which have some constraint of the network such that they are inequalities with some constraints that way. EJ bar equal to 0 for all J belongs to 1 to J. So these attributes constant are constraints which are equality constraints. Next you have alpha t belongs to A omega t for all t. So this is your action set that could vary with time at each step. And then Q stability. So these are your inequality constraints. These are your equality constraints. This is your action set at each time t. And then the Q stability. That means the Q stability basically means that at time, as time tends to infinity or at steady state, your Q don't blow up because you'll have a finite amount of Q storage. So uh, yeah, your system doesn't blow up. So, but we have not mathematically defined what the stability of Q is. So this we have to define Q stability, right? So this is one type of problem that we'll have to solve. We'll model our networks to solve this so as to optimize the some function y0 hat such that uh, you decide the scheduling policy of that. So instead of FIFO, we decide at each time which packets to be served, right? That is what alpha t is. So we are minimizing over alpha t, right? The second objective is more general than the first, right? So here we have to optimize convex functions of time averages. Okay? So let us have some convex functions of fx, g1x, and so on, glx. These convex functions are from Rm to R, and x is a convex subset of Rm. I'll define the problem that we want to optimize. Minimize y0 bar plus fx bar where X bar is the time average of the attribute XMT that we have defined here. This, okay, such that the constraints are y time averaged YL vectors plus GL X hat less than or equal to 0, EJ bar equal to 0, X bar belongs to closed set X, alpha T belongs to A omega T for all T, and stability of Qs. A similar problem where you have similar problem is problem 1, but you have some penalty in the cost function. By using some attribute, right? Um, you have your inequality constraint with the with another penalty function. You have your equality constraints, your bounded penalty attribute, your action set, and the stability of Qs that we are still to define. And we have to define, we have to mathematically define what the stability of. So these two problems can be viewed as stochastic programs and are the analog of the classic linear programs or convex programming or static optimization thing. A solution is an algorithm for choosing control actions over time in reaction to the existing network state, such that all of these constraints are satisfied and you minimize the quantity that we have chosen, or you choose the control action such that the objective function is minimized as small as possible and you have met all the constraints. These type of problems, they have many applications in the area of interest, mm, with no queuing networks to be ablaze. Like so, the stability constraints could be removed, but mm, we want the queues to be stable, and it plays a central role in the step of stochastic optimization. Okay, so here I'll try to introduce a term known as virtual queue. We'll sometimes define virtual queues so as to convert the problem into a different type of problem, right? Yeah. Uh, but once the virtual queues come up naturally, it will be good that I introduce it there. So I'll introduce two more terms here before going forward. These terms we have talked about previously in the previous class also, but we will again do it here once. So I'm define. So suppose X is a convex set, right? What does this imply? This implies that for all A comma B belongs to X, the line segment joining A and B also belongs to X, then X is a convex case. So mathematically, what you write is for all A comma B belongs to X implies GA plus 1 minus TB also belongs to X for all T belongs to 0 to 1, right? So basically some example of convex set is you have set which has no just perfect circle. You have A and B, but the whole line segment also lies in the side X. The first one is convex, right? Okay. Then we'll talk about fx is a convex function. What a convex function is. Convex function is, so before you define what a convex function is, you need to know what a convex set is. Convex, a function could be convex only over a convex set, over set X which is convex. Right? For all A comma B belongs to X convex, if you have f of TA plus 1 minus TB less than or equal to TFA plus 1 minus TFB, then fx, the function f, is a convex function. So basically, what you have is you have A, B, 2 points. Let your x coordinates be just the positive real, right? If it is positive, then it's a convex set. It doesn't matter. Now you have 2 points, FA, FB. You have a function which goes through this and this line. So this T8 plus 1 minus TB defines a point in between the line segment A and B. So T8 plus 1 minus TB. Now, if you look at this, the function value at f A plus 1 minus TB, this point, is always less than or equal to is the line segment joining FA and FB. And this point is, this is the value at TFA plus 1 minus TFB. Right? This is less than or equal to this value. Then we say that the function is a convex function. Now, some equivalence to this is if the function is differentiable, twice differentiable basically, then if f double dash of x is greater than or equal to 0, then we can conclude that f is a convex function. Okay. Next, I'll introduce a topic known as Lyapunov drift. And Lyapunov optimization. So before that, I'll denote these two problems. This problem is problem 1. And this problem is problem two. Well, these two concepts I'll discuss clearly in the upcoming classes. I'll just give a brief introduction of uh, what do you mean when when I say Lyapunov function, right? So the first step that we need to solve P1 and P2. The first step is to find points that satisfy the constraint. That satisfy the constraints. Okay. Next, we construct virtual queues. How do you construct these virtual queues? We'll go into that discussion later. But what you want is we'll construct these virtual queues such that these virtual queues help to meet the constraints either in steady state or some other, but we will define how to construct these virtual queues. Next is we define a Lyapunov function LT as the sum of backlogs of queues that are the actual queues, the actual network queues, which we have defined as queue, and also sum of the square of virtual queues, which we have defined in step two. This step two queues, these. We define this as the Lyapunov function, right? This Lyapunov function is basically a scalar measure because QTs are vectors. These two are vectors, right? So this is a scalar measure of network congestion in the system. If your L function is high, implies you have a congestion in system. If your L is low, this implies low congestion. This is the third step. So if L is high, this implies that at least one queue is congested. If L is low, it implies that all queues are not congested. We'll come back to these kind of how congested the implications are depending on what the value of L is later. But I'm just giving the steps of how do you do a Lyapunov drift or Lyapunov optimization given these general stochastic optimization type problems of P1 and P2. Right? Then we define delta t or the change in t as L t plus 1 minus LT. So this being the difference in the Lyapunov function from one time slot to the next time slot. If every control decision that we make uh, is to greedily just minimize this delta t, right? So if we minimize this delta t, what we try to do is we gradually consistently try to push the LT towards a lower congestion state, which intuitively maintains network stability, but we have still not defined what network stability mathematically means, right? So minimizing delta t at every slot is known as minimizing the Lyapunov drift. We'll see how this method provides usability for some particular examples of networks, and also these type of methods, usually the scheduling policy that comes out from these type of methods stabilize the given network. But still we have not solved the problem. So all we have done is we have found out points that help to ensure that the time average constraints are met and the queues of the network are stable. We still have to find the objective function to be minimized that is not yet incorporated. Like we've not decided or discussed what the objective function is, right? So y0t, which we have defined in the first problem. In the second problem, we have also defined an appropriate function, which is penalty. So that. So our fourth step would be, instead of minimizing delta t, right, we define a function known as penalty of t, and we minimize delta t plus v into penalty of t, where here this penalty is a function that depends on the objective function. The objective function of the optimization problem that we are trying to solve. This v is a non-negative control parameter. So if you choose v equal to 0, then you're just solving the algorithm of minimizing the drift. That is, you are finding a point which satisfies the constraints in the optimized problem and also give a stabilized queue. Choosing v greater than 0 includes the weighted penalty term and also allows a trade-off between your backlog reduction, that is queue stability, and penalty minimization, that is minimization of the objective function. Some preliminaries to this that we will require while discussing these kinds of topics are basically expectations, law of large numbers, etc., and basic mathematical analysis. Mm, And any requirement on Markov chains, convex functions, I've already discussed what convex functions are, or queuing theory, similar to the steady state waiting times that I discussed of MM1 queues. Uh, if those come up while some theorem, I'll try to present those there. And So, some of the key concepts that we will look through right now. One is law of telescopic sum. Suppose you have a function f of t defined over integer times. So t belongs to 0, 1, 2, so on. We have at any time t summation tau equal to 0 t minus 1 f of t plus 1 minus f of tau plus 1. This is equal to ft minus f0. So how do you get this? Is basically you expand this. Let us expand this inside. So first is f1 minus f0 plus second term is f2 minus f1. And as you can see, this f1 and f1 will get cancelled. Plus f3 minus f2. And as you can see, this f2 and this f2 will cancel. Similarly, f3 and f3 will cancel. f4 it will continue. Now the last term is f t minus f t minus 1, but the previous term is f t minus 1 minus f t minus 2. T minus 1 and t minus 1 cancel. There is no term here because it has stopped here to cancel out this term, and there is no term here because it started from here to cancel out this term. So these two terms will get. So hence it will be ft minus fc. So this is your telescopic sum, right? So if you have telescopic sum, then the telescopic sum is just equal to the difference between the last term and the first term. This main idea helps us to control the change in the function at every step behind the Lyapunov drift arguments. The summation of q squares that we'll have this function. We can write it as telescopic sums. Okay. The next thing that we'll need is law of iterated expectations. So if you have random variables x and y, expectation of x equal to expectation of x, sorry, x condition bar. So strictly speaking, this law of iterated expectation only holds whenever the result of Fubini's theorem. Fubini's theorem is a method by which we can interchange the integrals. So the cases where we are allowed to interchange the integrals are basically when absolute value of the random variable is finite and or expectation of min x from 0 is greater than minus infinity, or expectation of max. So either one of these three is satisfied, then the Fubini's theorem is valid and you can interchange the integrals. But in the cases that we see right now, all of the random variables that we are working with would satisfy one of these three. So the law of iterative explications would go through without any issue. No need to check each and every time whether the Fibonacci theorem is satisfied or not. This outer expectation here, this is distribution over y. This is a distribution over x condition on y. Next is opportunistically minimizing an expectation. Minimizing an expectation. So basically what happens is you have your network system. Whenever you take or you choose in control action alpha from some action set A omega, mm, so you choose alpha t, which is your action from your action set A omega, right? You incur a cost of C alpha omega, which I'll just say a general cost function. I've not specified what the function for is. So what is our goal? Our goal is to determine a policy of choosing this alpha such that you minimize the expected value of the cost return C alpha comma omega, right? You choose a series of these alphas with the expectation is taken with respect to the distribution of omega, because the only randomness in this cost function comes from omega, not from alpha, because alpha is the action that you are choosing, right? So for simplicity, just for the more simplest case, we will assume that for any given random outcome, omega, there is at least one action, alpha omega min, which minimizes the cost function. And I know what this alpha omega means, right? Then the expectation of C alpha omega is basically minimized by taking alpha omega min at each step t. So what I'm saying is from alpha t belongs to A omega, this set, you have alpha omega min t such that C alpha omega min t comma omega is less than or equal to C alpha omega omega, where all alpha omega belongs to A. So alpha min omega minimizes the cost function at each and every step, right? Now taking expectation on both sides, because expectation is preserves inequalities, that means it is monotonic. So expected cost function is the minimum if you choose alpha omega min at each and every time step, right? So while designing the drift minimization algorithms, we will be using this thing that at each time step you greedily decide what is the best possible action that you can take that minimizes the cost function at that time. If you do this at each and every time step, then the expected time is minimized, right? The next is Jensen's inequality. Jensen's inequality is basically the inequality over a convex set X, which is a subset of Rn or R, or it will be the full space, it will matter, and a convex function Fx. So Fx is a convex function, and X is the convex set. Let X be some random vector which takes values in the convex set, and we assume that the expectation of X is well defined, finite, and everything that needs to be. Okay? The expectation of X belongs to this complex set, and f of expectation of x is less than or equal to expectation of f of x. So this basically is your Jensen's. And similarly, we'll be using lim sup and lim min, but these could be interchanged with limit anytime and it will not affect the main idea. But the reason that we are using lim sup and lim min is basically you might encounter functions where limits don't exist. So basically, if lim sup equal to lim min, then that is your limit of that function. But what if you take a function such as cos x, cos x, as x tends to infinity, there is no limit of cos x as it oscillates between -1 and +1, right? So what you have is the lim sup of cos x is basically 1 and lim in cos x equal to -1. So if you encounter with some functions in where limit do not exceed, we'll shift to lim sup and lim. Some properties of lim sup and lim for functions are, so if you have functions ft, gt that satisfy ft less than or equal to gt for all t, then lim sup of ft is less than or equal to lim sup of gt. So lim sup preserves monotonity. Similarly, lim inf of ft is less than or equal to lim inf of gt. So basically, both of them present inequalities basically are monatomic in nature. Monatomic in nature. Second point, for any function ft, you'll always have that lim inf of that function is less than or equal to lim sup of the function. And the equality will only exist if the limit of the function exists. Minus limit. You have ft and then lim sup ft equal to minus lim inf minus ft, and similarly lim inf ft plus lim sup minus ft. Okay, so that is it for today's class. In the next class, we'll discuss about introduction to queues. So basically, the stability of queues, we'll discuss the stability of these queues. So today we discuss some general stochastic optimization problems, how the general model is. So we define two types of stochastic optimization problems, and then we told that what are the steps that we'll be using to solve these two types of problems using Lyapunov drift and Lyapunov optimization, the four steps. So what the drift means, what is the Lyapunov function, and all. And then we gave some preliminaries of lofty use for fixing, lofty trade expectation, opportunities minimizing, general inequality, and limits of lineage. In the next class, since both the problems that we have defined today have a constraint on stability of Qs, and we have not yet defined mathematically what the stability of Q means. So in the next class, we will uh, define the stability of Qs. Thank you.